were doing that baseball bat problem. I'm gonna reverse the picture so that the ball is coming from here. So it was a 1 kilogram ball coming at, I can't read his handwriting. What's the speed of the ball? I can't read this. Yeah, the handwriting can use some help.
I don't blame you on that. I think it's 30 meters per second with 0.8 seconds per second.
This is
That's 100. That's 100. The ball's going at 100 miles per hour, 35 meters per second.
45 meters per second?
Yeah, that was what we agreed
Oh, okay, so 0.15 kilograms, 45 meters per second, and this one was 1 kilogram going at, I can't read that one either, oh God. 30 meters per second, I think. And then from here to here
I can read
is,
this, that's all that matters.
here to here is 0.8 meters. And then I think from here to here was 0.5 meters. Okay, so remember we're doing momentum conservation, right? So the momentum is gonna be, momentum initial is momentum final. So what was the initial momentum of this guy? 1 times 30. The initial momentum of this guy is 0.15 times 45 is equal to, at the end, the ball turns back. So after the collision, it looks something like this. This is moving forward at VCM, and then the ball returns back 0.15 with some V final. So then this one is gonna be 1 times VCM plus 0.15 times V final. I think we simplified that, right? So what was the final thing that we got after we simplified the left side? 30 minus, what is this? 23.25 VCM plus 0.15 V final, okay. Then we did the angular momentum conservation. That one was, it was harder, right? You have to do the I, the moment of inertia of this guy. So once we did the angular momentum conservation, what did we get for that one? At the end, like what's the final equation that we got? Some number, or did we not get anything? We don't have it? Do you have it, Brian?
I think how we set it up was we get I equals LF, where I initial of the mass plus omega initial minus the mass of the ball times the velocity of the ball
Times
the
the
height of the ball
Yeah.
equals to m subscript b times mass of the ball times the velocity of the ball.
And then did we put in numbers there?
No, I just have the numbers on. Maybe we did. I'm not too sure.
I thought. Oh, we stopped at the equation?
Yeah.
We never put in anything? Oh, okay. So then the moment of inertia of the bat, oh, I remember now, we had to integrate the bat. Did we upload Monday's video? Oh no, because I was gonna see where, I thought I talked about that. I had to reintegrate the bat, then shift it.
I can show you the video.
Did we do that already? Or do I have to do it now?
We did integrate it.
We did so for ICM.
Oh, ICM of the bat, because remember the mass changed? The ICM of the bat. Because we changed the mass from 4 kilogram to 1 kilogram and the length from 4 meters to the length of this, right? Didn't we change it?
Yeah.
Yeah.
ICM. What did we get?
We got 1.717 kilograms.
1.717.
7.
Oh, now I remember. we first did a perfectly inelastic collision with the bat, didn't we? Ah, okay, where it got stuck, the center of mass shifted. Okay, now I remember. Then it went. Then I said, let's do the bat with an elastic collision and mimic a baseball hit, right? So yeah, we did do the ICM, but now we have to shift it to the center of mass of the player, right? Okay, now I remember. So then the I initial is going to be 1.717 plus the mass of the bat, which is 1 kilogram, times the shift amount from here all the way to here, which is 1.3. 1.3 squared.
Oh.
Right?
The sorry, mass I gave you was the shift amount.
Oh, we already did the shift? Oh, okay. So what was the ICM then?
The ICM before was 2/75 ml squared.
Okay. 2/75 mass times length. What was the length of the bat?
Well, one meter.
Oh, yeah, okay, 1 meter. And the mass was also 1 kilogram? No, something is.
That's what you have.
Oh, the mass of a typical bat was 1 kilogram?
Maybe 10 kilograms.
You sure?
Yeah, that's what we have now.
Oh, and then the length was also 1 meter?
Yeah.
Oh, okay. So then 2/ml squared. So the ICM is actually very small. But then when we shifted it, we got the 1.717 you were saying. Oh, okay. So then it's gonna be 1.717 omega initial. Oh, okay, so then what is omega initial? That's not given to you because when we looked up online, it just told us the tangential velocity of the bat. And we said, oh, let that be the velocity at the center of mass, right? So how do I find omega then? I need the rotational speed of the bat in radians per second. So I could use what? V tangential is R omega. V tangential is 30 meters per second. What's my R? Is the distance of the center of mass from the center of the player, right? This is the center of player. Right, so that's going to be 1.3. And that's my initial omega, right? So then that's 30/1.3 is omega initial. So then I could put that in here, omega initial 30/1.3. I initial, omega initial. Okay, now we're going to do the MVH of the bat, because the angular momentum of the bat, see the angular momentum of the bat is into the board, but the angular momentum of the baseball is out of the board, right? It's fighting against it. So what is MVH? The mass of the bat times the velocity of the bat times h. And what's my h initial? Around which point is it gonna rotate? Around here, right? So it's gonna be the angular momentum with respect to that point. So then that means the h initial is the same thing as the r here, right? 1.3. All right, everyone following? Moment of inertia of the bat shifted. The omega of the bat from the v tangential, the mass of the ball, velocity of the ball, h initial. Then the I final of the bat still stays the same number, 1.717. Omega final, we don't know, right? That's what we want to find. And then plus m is 0.15. V final, we don't know, and the h is what? Still 1.3, right? The distance from here, the vertical distance is still 1.3. So the h is 1.3. V final, you don't know. So there's basically two unknowns there, right? So we calculate this guy.
Where is the MVH coming from?
The angular momentum. Remember when something is like this, and then it hits a rod, its angular momentum is R crossed into P. R, P, sine of the angle. And then R sine of the angle is the H, which is this thing.
Yeah.
So then it's just RP, hold on. R sine of theta is the H, then P is P, HP, which is Hewlett-Packard,
Points.
right? So Hewlett-Packard is essentially angular momentum. The distance times the linear momentum. You thought HP stood for Hewlett-Packard? No, angular momentum. Right? HMV. Okay, now let's see. Oops, the phone is stuck.
So you're using both forms of angular momentum?
Oh yeah,
Okay.
because this one is not a spinning object. It doesn't have that kind of angular momentum.
Uh-huh.
But it has angular momentum because it's hitting this guy away from the axis of rotation. You see?
Mhm.
So by virtue of the fact that there's a R crossed into P is not zero. That's why it has angular momentum, not because it's spinning like this.
Mhm.
Now on top of that, I can say the ball is also spinning. I can make it more complicated because when a baseball pitches it, he might give it a slicer, breaking ball. So the ball might be spinning and coming and hitting the bat, or spinning the other way. So then it's going to have two kinds of angular momentums, MVH and then I omega, whatever the spin that the pitcher gave it. Right? Then of course when you hit it, that changes the problem of what happens. You see? So no pitcher is just going to give you a fastball. They're always going to throw this kind of spin, so it has this kind of angular momentum, or they're going to hit this one, or they're going to go this one. Which one is the slicer?
Slider.
Slider is down. Breaking ball is what?
It could go down or at an angle.
At an angle. Yeah, there's a whole physics of them. No, it's crazy. Okay, so now let's see here. 1.717 times 30 divided by 1.3 minus 0.15 times 45 times 1.3. Okay, 30.848. And then this is just simply 1.717 omega final. And then this is 0.15. 0.195 omega V final. Okay? Okay, what else? Oh, now this is angular momentum conservation, right? How many unknowns do we have? VCM, V final, then we have the omega of the bat. 3 unknowns in a conservation. We're doing totally elastic collision, right? So we did conservation of angular momentum. This equation has 2 unknowns in there, omega and V, right? So this is the second equation. It has 2 unknowns. This one has 2 other unknowns, but it doesn't have the omega, right? Because linear momentum doesn't care about omega. Now we need a third equation, kinetic energy conservation. The initial kinetic energy of the problem equals the final kinetic energy. Okay, so what kind of kinetic energy does the bat have?
Rotational?
Right? The rotational kinetic energy. So I can do 1/2 I initial omega initial squared. And then what kind of energy does this guy have?
Translation?
Translational. Do I subtract the energy because it's going the other way? Or does energy not care about direction? Huh?
It's in joules, so.
In other words, should I do 1/2 I omega squared minus 1/2 mv initial squared? Because it's going opposite direction? A bit tricky, right? With angular momentum, you do. But remember, kinetic energy is actually 1/2 mv initial. V initial is negative 45. But if you square a negative, it gives you what? Positive. So this is not the negative, this is the negative. But it doesn't matter for energy. Whether you're going to the left or to the right, the direction doesn't matter. See, energy doesn't care about the direction. Angular momentum and linear momentum care, right? See the negative? Negative, because they're vectors. They care about direction. But energy doesn't care. You see? So then it's just that. And then that's equal to 1/2 I omega final squared plus 1/2 m v final squared. So now we could put in everything. I could get rid of the halves if I want. And then I initial is going to be your 1.717. What's omega initial? 30 over 1.3, right? Plus m. M is going to be the 0.15 times v initial, which is 45 squared. And then this is going to be 1.717 is I final, right? Omega final squared plus MV final is going to be your 0.15 V final squared, right? Okay, then I can calculate that. One 1,218.129, 1.717 omega final squared plus 0.15 V final squared. See if I accounted for all the possible kinds of kinetic energies. Kinetic energy rotation. This has kinetic energy rotation, kinetic energy translation. Does this have translational kinetic energy? Oh no, it doesn't, because you're holding on to the bat and you're rotating it. It has only rotational. Now if you hit it and you let go of the bat, like some players, they lose handle of the bat, right? Then the bat starts going forward also. Then it would have translational. So on purpose, I didn't put in the translational energy of the bat, because you're still holding on to the bat.
So it's moving around a pivot point.
It's just the moving on, so it only has kinetic energy of rotation.
Wouldn't you be able to replace the omega final with V final over R?
We could do that. Then I would have to replace it here, because if the question is asking find VCM of the bat, if it's not interest, in other words, the VCM and the omega final are actually interrelated, right? They're not independent from each other. Hold on. Oh yeah. It's actually, we only have two independent unknowns in this problem. Oh, that means this equation that I have is wrong. It's wrong. It's awesome. I love this. Because this and this are related. VCM is equal to R omega final. Wonderful, isn't it? You analyze it. So what we did Monday, late Monday, was wrong. Right? So these are interrelated variables. So that means what? Linear momentum is not conserved in this problem. Linear momentum is only conserved if at the right before the collision I let go of the bat. Let's say I'm rotating it and then I lose control. And so now the bat is spinning, hits it, and now a bat is freely floating object, right? It's ready to rotate and translate. Then linear momentum is conserved. But then omega and VCM are independent variables now because it's in the middle of the air. You see? You see? If I let go of the bat, then these are independent. But if I'm still holding on, I'm the pivot point. So linear momentum is not conserved. Okay, but is this still correct? This one minus this one, angular momentum? Yeah, that's correct. Is this correct? Yeah, it has angular momentum. This has angular momentum, yeah. And this is also correct because I didn't put in translational. So actually I only have two unknowns. Okay, at this point, if the problem asks for my VCM instead of omega, I can do what Eduardo is suggesting. You can replace omega by saying omega is VCM. VCM is omega times 1.3, right? Yeah, this is 1.3. So then if you want to get rid of this omega and that omega, you can say VCM is omega final is VCM over 1.3. Then substitute it here, substitute it here. And then you just have VCM of the bat. Because in this problem, we were more interested in the velocity of the bat. I'm interested if a bat is coming in and at 30 meters per second, what happens after it hits the ball? Does it slow down? And what is the final speed? You know? So I am more interested in VCM. Okay, so then what's my thing? 30.848 is equal to, then I put omega final is VCM over 1.3. Then I put the same thing here. 1218.129 VCM over 1.3 squared plus 0.15 V final squared. Okay, so how do I solve this? Well, you kind of solve this the same way that you do in a chapter 9 problem, elastic collision, right? You do a substitution, you substitute it into the other thing. So you can say, let's substitute for V final and then put it in here, right? So you're gonna get here 1218, 1.717 over 1.3 squared, VCM squared plus 0.15, and then V final is gonna be what? Take this to the other side, right? So V final is gonna be what? 30.848 minus 1.717 over 1.3 VCM, right? Over 0.195, that's V final. And then square that. And then don't worry about simplifying it. Put it in solver and let the solver solve it for you. Okay, so remember it's going to give you two solutions. One of the solutions to this should be the original V, 30 meters per second, right? So on the TI-89, it will give you both solutions at the same time. So make sure you input this right. Solve 1,218.129 equals 1.717 divided by 1.3 squared times x squared plus. Oh, guys, sorry.
Can I just finish writing one last thing?
Yeah, one last thing. Okay, Jason. Okay, so 1.717 over 1.3 squared plus times x squared plus 0.15 times, and then this thing. I did get two answers. Oh, thank you. I did get two answers. One answer is 30. See, I love this because it gives you two answers same time. So, and then the other answer is 10.7 meters per second. The bat slows down. BCM, 10.7 meters per second. Alright, now from there we can calculate V final of the bat, the V final of the ball. This is VCM of the bat. So it went from 30 meters per second to 10, which is still fast, right? So yeah, that makes sense. You hit the ball, and then after that you keep swinging forward, but the velocity decreases. And then the omega, where do I put it? Well, I could take this, put it back into here, because remember this one was omega, right? No, hold on. Not omega, I meant V final, right? This one was the V final. So if you take this and put it here, that will give you V final of the ball. So V final ball.
Make sure they don't mix together.
Thanks.
$85. Wow. The ball goes back at 85 meters per second. It's crazy fast, right? So what was the speed of the ball coming in? 45 meters per second?
Yes, sir.
Which was around 100 miles an hour, right? So this is gonna be almost double that, almost 200 miles an hour the ball is gonna go back. And remember, we used realistic numbers, realistic speeds. We tried to make it as possible, as realistic as possible as we can make. So if you swing it, hit it at the right place. Of course, I'm assuming that you're hitting it at the right place because the bat is round, so you might hit it at the bottom or this. We're not taking that into account. I'm assuming it hits it right straight on and then goes back. But if you're swinging, it might hit the bottom and then be a ground ball. You know, if you hit the way top, pop up fly. So that we're not taking that into account, the angle, you know. But the answer that we're getting is pretty accurate. Oh, the other thing I'm assuming is the collision is elastic. In real life, it's probably not elastic. There's some absorption of energy in the vibration, right?
Yeah.
So some of the energy of the system is lost.
The back gets dented and stuff.
The
so-
back gets dented, yeah, you
Ball
absorb the
gets-
energy in the sound wave, you absorb the sound energy. So the energy in real life should not be, so this is probably a little bit too fast to bounce back at that speed. Then we can say, okay, if the initial velocity is 85.272 meters per second, and let's say it goes up at 50 degrees, and your hand is at a height of 4 feet, and there is a fence, 200-foot fence. That's the Green Monster in Boston, right?
310,
Huh?
310.
How many feet away is it from you?
310.
310 feet. What's the height of the fence in the Green Monster?
570 feet,
70?
yeah, 60.
Okay. So if it goes at 85, this is meters per second. Is that a home run? Then it becomes a chapter 4 problem.
Yeah.
You know, so that's a good final problem, huh? Do that, solve it, put it back in there, see if it's a home run. But of course, the problem has to give you the height, the distance, and the angle. All you know is the final velocity of the ball going back. You see? So this was an example where momentum was not conserved, but the two V's were conserved. The first example we did was also like that. It was the ball coming and getting stuck and going together, right? Going together like this. In that case, which quantities were conserved? Oh, in that case, linear momentum was conserved, remember? Linear momentum was conserved, but angular momentum was conserved, but not energy. So this is like the second example we're doing. So in this case, L is conserved and kinetic energy is conserved, but not momentum. You see, because you're holding the bat. The other one, the ball came and nobody was holding the bat. The bat was sitting on a table. And the ball came and stuck to the bat. And together they rotated around their new center of mass, right? So since it got stuck, it would be inelastic. So in that case, linear momentum got conserved. Angular momentum got conserved, but not kinetic energy. See, so it's slightly different. Then there's the example where all three could be conserved, okay, which is this one here. On my test review questions. Is this test 5? Yeah, test 5. Yeah. All three, this is all three being conserved. Sticky ball with a mass of 3 is traveling at 2. It is 30 centimeters above the central axis of a ruler, which is 1 meter long and has mass. The sticky ball collides and sticks. Oh no, if it sticks, it's like this one. If it sticks. 6, in the previous problem, if the collision takes place perfectly elastically. Okay, so now you can have a case where the ball comes, doesn't stick, and no one is holding the bat. You see? In the baseball case, the person is holding the bat, but the bat could be lying on the ground. And the ball comes, hits it, then maybe bounces back, and the bat rotates and translates. So what's gonna happen? That's this example, right? And I have video on it online, so you can watch it. So in that case, what's gonna happen? You're gonna have 3 kinds of kinetic energy at the end, right? You're gonna have the bat, the ruler is gonna have translational energy, the ruler is gonna have rotational energy, and the ball is gonna have translational. So three energies, you see? So this is all 3 of them are being conserved. K, linear, and angular. This one is the other possibility. You can have a case where kinetic is conserved, then linear momentum is conserved, but not L. So you see, it's like all the possible permutations of that problem. You can have L conserved, KE, LKE, LP. How about the examples that we did last week? They were considered not non-collision problems. The circular merry-go-round and the cockroach walking. Right? So you're given a disc that's rotating, a cockroach is walking on that disc, and then the cockroach begins to stop, and it comes to a full stop. Which of the three are conserved there? How did I solve the problem? Remember what conservation law I imposed on the problem to solve it? Don't remember? I initial, omega initial is I final, omega final, right? I imposed the conservation of angular momentum. So he's walking originally, and then he finally comes to a stop, right? I imposed conservation of angular momentum, but I said, what's the work done by the ant, by the cockroach or the ant, whatever. So the energy was actually gained. Was it gained or lost? See, the cockroach stops, the thing starts speeding up. It's actually gained, right? Yeah, it should be gained. The kinetic energy should be gained. Did we solve for that? The changing kinetic energy of the cylinder? I'm not sure if we did. Your homework question from the book is going to ask you that. There's going to be a lady walking on a disc, and then the lady's going to be speeding up or slowing down. And then it's going to say, what's the work done by the person? Then you do changing kinetic energy. Depending on whether the lady is slowing down or speeding up, either the kinetic energy can be gained or lost, depending on what they're doing, right? So in that problem, only angular momentum is conserved. L initial is L final. The kinetic energy could either be greater, the kinetic energy final could either be greater, or it could actually be less than initial kinetic energy, depending on whether the person walking stops or speeds up, you know. But linear momentum in that problem, is it conserved or not? P.
Sorry, can you repeat the question?
Linear momentum. What happens for that linear momentum?
Linear momentum.
It's conserved.
No.
The initial linear momentum of the system is 0 because there's no translation. The final linear momentum of the system is 0 because there's no translation. So linear momentum is irrelevant in the problem because there's only rotating a disk, and I'm walking on the rotating disk, right? There is no translation going on.
Oh, I see what you're saying.
There's only angular momentum.
The thing itself's not moving.
Yeah. So
It's
it's
just rotating.
irrelevant in that
So
problem.
linear
In that
momentum
kind of a
makes no
problem,
sense.
it's irrelevant.
Even the walking of the.
Well, the walking will cause you to have an angular momentum, L crossed into R crossed into P.
Because of the rotating disc.
Yeah, because you do have linear momentum, but what's more important is the angular momentum that you have by virtue of your linear momentum.
Okay.
You see? Because you have a linear momentum as you're walking, you have angular momentum. That's the one that's more important, not your linear momentum.
So there's no way like you could run straight on a platform and not.
Okay, now if you're walking and the platform you're sitting on is on icy surface and not stuck to the surface,
Right.
then it's different because as you walk, the thing is gonna start sliding on the surface to keep the center of mass constant.
Oh.
see? So then linear momentum might have something to do with it, you see? But if it's stuck to a post, then linear momentum doesn't matter for that problem. Only angular momentum matters. The other problem we did was this one, where you had like this, then I added something, right? So for that, what is the conservation? Was it kinetic energy conserved or the angular momentum conserved? I think I went through a whole long explanation comparing this to the post problem with the chain, right? That one is kinetic energy is conserved, right? But not angular momentum, right? If I'm correct, yeah.
Yes,
Kinetic energy conserved, but not angular momentum. And linear momentum is irrelevant, again. Here, angular momentum is conserved. Kinetic energy is not. It's gained, right? But if I take the weight off, then the kinetic energy is lost. You see? If I take the weight off, if I reduce the weight, it's going to start slowing down and start moving, spiraling outward. You see? Then the kinetic energy final is less than kinetic energy initial. So this is kind of like this guy, where depending on how you stop or you speed up, the kinetic energy can change, but angular momentum is conserved, angular momentum is conserved. Here, kinetic energy conserved. Here, linear momentum is irrelevant, linear momentum is irrelevant. You see? Okay, now, how about a case where all three of them are conserved? Well, that's example 6. All three of them are conserved. So something comes, something hits it, bounces back, that thing starts spinning and translating. All three are conserved. How about this one? A hollow sphere of mass 6 kilograms and radius 1.2 is rolling without slipping on the horizontal surface with a velocity of 2. Okay? So you've given a ball, its V center of mass is 2 meters per second, and it's rolling without slipping. That means if it's rolling without slipping, omega final is omega initial equals what? You already know the omega initial, because if it's rolling without slipping, the V tangential at the edge is what? 2 meters per second, right? So omega initial is 2 over the radius of the ball, right? So what kind of kinetic energy does this have? Translation and rotation, right? So then it's going to go hit another ball, maybe a different shape, maybe a different radius, right? So then it says, it collides perfectly elastically. So what's that clue? If it collides elastically, that's a clue that what's conserved.
Linear momentum?
No, elastic is a clue for something else. Kinetic energy is conserved, right? Kinetic energy is conserved with a solid sphere. So it's a different shape because this was a hollow sphere. Mass is 10 kilograms, radius is 0.8 meters. You see the radius is even different. This is smaller. So, so it's a little bit smaller, but that one is standing before it hits it, right? So then it says find V final and omega final of both balls after the collision, right? So this guy is gonna come, dum, 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 hit this, boom, while it's still spinning. And then this guy is gonna get a kick. This is the most similar to what happens when billiard balls hit each other, right? It mimics that. A ball is coming, but in the case of billiard balls, they're all the same size and same weight.
Yeah, so they hit the same point. There's only one point of contact.
Yeah, but here it's a little bit like one is bigger than the other,
Yeah.
so yeah.
It hits with an angle.
It hits with an angle, that's
Yeah,
true.
with the pool table, because they're the same size, it only hits along one plane.
Yeah.
Which is the center of each billiard ball.
Yeah, exactly.
So that
Yeah.
way they can't tick off or.
Yeah. So then, what quantities will be conserved in this? This guy's gonna hit this guy. After the collision, this guy might start rolling backwards. And then this guy might get a forward kick. So V final 1, V final 2. So what quantities are conserved? In this one, sometimes when you're not sure what quantities are conserved, ask yourself, how many independent variables are there that I need to solve for? If you've got three independent variables, then you have to have three things conserved.
Right.
If you've got two independent variables, two things must be conserved. And if you have only one, then one of them only can be conserved, you see? So that's like a clue.
Yeah.
So if this is going like this, the final one, that's one unknown I have to solve for. Another unknown, how about the rotation of this? Is that another independent variable, or are they related? Oh, let me call this 2 and then 1. Is the rotation rate of that related? Or is this an independent variable?
It's not independent. Wait, the V tangential and speed should be related, aren't they?
Well, you tell me. We've had long lectures on rolling motion, and are they related?
Would it have to be?
Since the floor that it's traveling on is, what did you say that it was?
It's no slipping.
Yeah.
Yeah, it's rolling without slipping. So originally it's also rolling without slipping, right? And then we're assuming after they collide, the problem is assuming that it's also rolling without slipping.
So they'd have to.
So if they're rolling without slipping, are they related? Yeah.
Yeah.
Omega V final 2 is just V final 2 over the radius of that object, right? And then here, this is going back and spinning back. So then omega final 1 is what? V final 1 over R1. They're related. So how many unknowns do we have? Technically, we just have two unknowns, V final 1 and V final 2. Once you get that, you can get the omega final. So if you only have two unknowns, how many quantities of the three can be conserved? Only two. Now decide which two should be conserved. Linear momentum, angular momentum, or kinetic energy.
Kinetic energy 1, right? Because it's an elastic fluid.
Okay,
Yeah.
kinetic energy initial equals kinetic energy final.
I want to say linear.
So now between, you have to decide between linear momentum and angular momentum.
I want to say linear momentum, but I could be wrong.
We've seen a lot of cases where linear momentum is either not conserved or it's irrelevant. So let's give linear momentum a little bit of love. You know, we're ignoring it so much. Therefore, the love we give it in this problem. Linear momentum is conserved, and then we say angular momentum, we don't need you.
All right.
We diss the angular momentum in favor of the linear momentum. No, I'm just kidding, you know. It's not.
Is this-
But I made it like a little story because we got P being ignored so much. We got to balance the scales here.
So is this like when like a billiard ball is like rolling and strikes another one and it stops rolling?
It could be like a billiard ball going and hitting a basketball, maybe different sizes, different
Right.
weights, different shapes, you know.
And it just stops.
Well, I don't think it's going
Uh,
to stop. I think it's going to keep going. But
The rolling
because of
motion.
rolling friction,
The
it's going to
rolling.
eventually slow down. Yeah, yeah.
Okay.
But that one, don't worry about it. Yeah. So, therefore, something must be causing the angular momentum to not be conserved. If we can only conserve two of the quantities, what's causing the L to be not conserved?
I said earlier a mass difference.
Is
No.
there friction?
That means the total net external torque on the system while they're colliding
Is not there.
must be non-zero, right?
Ah.
That's your key. Torque external is the change of angular momentum of the system over dt.
That's fine. Like when a billiard ball hits and it stops spinning.
It could stop maybe in some cases that this hits it and stops spinning, but does it still go back or without spinning?
Well, I mean, they could do a lot of things, but.
Yeah, but I'm assuming that it's not sliding. I mean, it's not slipping.
Right.
Let's assume that the collision is non-slipping motion. But in real life, a lot of weird things could happen. It
Yeah.
could hit it and just slide afterwards, you know.
Yeah.
But forget that, yeah. So I guess what I'm saying is why in this system is now the angular momentum not conserved? Now, which cases did we see where angular momentum weren't conserved? Actually, I think the chain and the post was the only one so far from all the examples where angular momentum isn't conserved. What was the key to understanding why angular momentum isn't conserved in the post?
The angle between the.
Right? Remember the R? And then when you hold the chain is exerting a force towards the edge of the thing.
Yeah.
So R crossed into P was not zero. Okay, so when you can find cases where R and P are not necessarily anti-parallel,
You mean it?
if
you
there's
mean
an
it was
angle,
zero?
then it can be conserved. It can be non-conserved.
But the angle between
I
the.
think like if you put two circles right here, like there is a tangent line, and then you connect the tangent line to.
Yeah, so
to the
let's imagine
same-
what's happening when two balls, right at the instant that two balls are hitting each other. Imagine they're slightly different in size, but I don't think the size difference is the main key here, you know? The main key is that there's something going on with friction here. Right? So this guy is hitting that guy at a certain angle, and this guy is hitting this guy at a certain angle, but then this guy is hitting this guy trying to make this roll backwards, and maybe the friction on this guy is this way, Fs1. Right? Because it's getting a hit from that ball this way, so now that thing is going to make it go this way, right? And then the friction says, oh, okay, I'm going to try to prevent you from going that way, so the friction is this way, right? So then, this guy is the opposite. This guy's getting a force this way, and then the friction is this way, Fs2. Is one of these forces causing a torque on the system? Huh? What's R crossed into P? The R is measured from the rotation axis of each one, right? This is R. This is R. Oh. So this ball is experiencing a torque, right? Which way is that? R crossed into F. So the torque is out of the board, right? See? So let's call that R1, right? It's experiencing a torque out of the board. How about this one? R1, R1. R1 cross into Fs1, right? Out of the board. R1 crossed into Fs1. So in that case, it's just going to be, because the angle is 90, so then Fs1. How about the torque on this guy? R2 crossed into F2, right? Crossed into F2. There's a certain angle here depending on the size of the balls, right? So sine of, let's say, whatever angle that is, right, theta. And then the torque due to this one, or into the board, right? Yeah, this guy receives a torque into the board. This one is out of the board. Out of the board. This one is out of the board. So this one is into the board, right? Or so yeah, so that one is negative. R2 Fs2. If the net torque is not zero, what's going to happen? The angular momentum is going to change, right? So what's going to happen? Is the net torque zero? No, because this and this are in the same direction, right? R cross into F1, so it's actually R1 F1, right? Sine of theta plus R1 Fs1 plus R2 F2 sine theta minus R2 FS2. Are FS1 and FS2 equal? The friction force on them?
No.
No, I think it's whatever it needs to be so that the balls turn back their direction without slipping. So I don't think it could be the same. You see? So these ones don't cancel each other, right? And are these ones the same? Yeah, F1 and F2 are the same because it's an action-reaction pair. This guy hits this guy hits this guy. So F1 is equal to F2. So that one we can replace by F1. But still, the whole point is that there is a net torque on the system. That's the whole idea. If there's a net torque, angular momentum is not conserved. Only linear momentum and kinetic energy. Let's see. So you can get this. So how do I do that problem? I impose two restrictions on it. The linear momentum is conserved, right? And then the kinetic energy is conserved. That's it. But how is this different than the chapter 9 problem then? A block goes, hits another block, and then bounces back,
They're rotating.
right? That one also, kinetic energy is conserved, linear momentum is conserved. This one also, kinetic energy conserved, linear momentum conserved. Here, is angular momentum conserved?
Yeah, technically
It's irrelevant.
Yeah.
The initial angular momentum is 0, the final angular momentum is
Yeah.
0. See, now it's chance for angular momentum to be irrelevant.
Yeah.
You see?
Huh.
So, but how are these two problems different then? There's a slight difference. When you do the kinetic energy of this guy, you have to take into account its translational energy and rotational energy. Translational energy and rotational energy. So what you should do with those kind of problems is come up with an equation for the total kinetic energy of the rotating object, of that object depending on its shape, right? So for example, if it's a hollow sphere that's rotating, what's the equation for its total net kinetic energy including translation and rotation? Kinetic energy, hollow sphere, total. So when you see a problem like that, just derive an equation. Half m VCM squared plus half I omega squared, right? Then the hollow sphere, what's the moment of inertia? 2/5 mr squared. No, sorry, it's hollow sphere, right? 2/3 mr squared, right? 2/3. Times omega squared. Then you're going to do, then you have r squared omega squared, right? Then you're going to do what? R omega is what? V tangential. And V tangential, if it's not slipping, is the same as VCM, right? So you get rid of omega that way. Then you combine them and you get what? 5/6 mv squared. And there you have it. Now when you do kinetic energy conservation, you no longer use half mv squared. You just use 5/6 mv squared. Okay? Then you derive another equation for the kinetic energy of the whatever other shape it is. Solid sphere. Then you start doing your kinetic energy conservation and linear momentum conservation using those new kinetic energies. Equations, right? But now, what would happen if a rotating baseball, let's say in midair, VCM, and then it has some spin. It goes and hits another baseball, but it's in the middle of the air. It's no longer on the ground. Now are all three conserved? Angular momentum, linear momentum, right? So now it goes, hits it, and then after the collision, this guy goes forward, right? Probably this guy also starts spinning, This guy goes back. It also spins this way. V1 final, the omega 1 final, and then omega 2, right? Now how many independent variables are there? Ball in the air, spinning, goes and hits another ball, so it's no longer rolling motion. This is a doozy of a problem. There's potentially 4 unknowns. Why? Because the V and the omega are no longer related. They have nothing to do with each other. Whoever threw this ball in the air, they gave it some velocity and they gave it some spin, random.
A curveball.
It's no longer related. You can't say V is R omega, right? You can say V is 30 meters per second and the pitcher is really good. He gave it a very fast spin rate, 4 radians per second, right? Then it comes and hits this, and then it's going to go back. So potentially, it could have some random spin going back. It could go back at some random velocity. This guy can go forward at some velocity, and then it could spin at some velocity. Now, how many things should I conserve here? There's 4 variables. The problem has to give you one of those variables, because we don't have enough things to conserve. Right? So it has to say, after the collision, this one spun at 2 rads per second. Right? Then it can say, find V2, V1, and omega 1. Should we do it?
3 of them conserved.
All 3 should be conserved now. So this is another example of all 3 being conserved, like problem 6. Problem 6, you have something coming, hitting a rod. The rod is twisting and then going forward. So the way you solve this is similar to how you solve 6, but slightly different. Slightly different. Okay? Let's say we want to solve it. Let's make it easy and give the balls the same mass and the same radius.
Are they the same size or okay?
Yeah, let's say the same radius, so we can just make it easy. 1 meter, 1 meter. Let's say 1 kilogram, 1 kilogram, 1 meter, 1 meter. This one is going at 30 meters per second, but it's spinning at 4 rads per second. So now, after the collision, you are told that this ball starts spinning at 2 rads per second. Find V2, V1, and omega 1. So this is our example 3. So this most mimics question 6 of my test review, right? So we got linear momentum conservation, right, which is going to be what? So 1 times 30. After the collision, you got what? 1 times V2, right, the mass. And then this one minus 1 times V1, right? Linear momentum doesn't care about the spin, right? So imagine this is in the air. Okay? So then you just have 30 is equal to V2 minus V1. Now angular momentum conservation. Okay? So what is the angular momentum of this guy?
MV.
No,
I
it's just
omega.
I omega.
L.
It's different than the MVH that we've been using, right? Because this one, those ones were like this. It hits a rod, and then we did R, MV, right? And then we did MVH, right?
Oh, the angles.
But here, the collision is head-on. Now, if you want to make it harder, you'll say this ball is like this and this ball is like this, and it comes and hits it at the grazing angle, right? And then you're going to have 2 kinds of initial angular momentum. You're going to have the spin angular momentum of the ball plus the MVH, right? The MVH. But if they're hitting head-on, from here, the center of mass and the center of mass are head to head, then this one does not have MVH, angular momentum, because it's just going this way. But it has this kind of angular momentum, I omega. You see? See complicated? No?
Well, no, yeah. That's good.
Okay, so you got your, what's I of that? Oh, then I need to give you the shapes. Solid, sphere. Let's say the only thing that's different between them is the shape. One is solid sphere, one is hollow sphere. Right? So then initial angular momentum of this is going to be what? 2/5 mr squared. Oh, that was solid sphere, right? I omega, right? And omega is going to be what? Into the board, right? So let's consider into the board as positive, right? So it's just going to be I omega, it's just going to be 2/5 mr squared omega initial. And that's the only initial angular momentum, right? Then after the collision, what's the angular momentum? This guy is into the board, so it's positive, right? 2/3 mr squared omega final. Oh no, the omega final is given to you. It's 2 rads per second, you see? Minus the angular momentum of this, since it started spinning backwards, is out of the board, so it's negative. You see? So then it's going to be minus 2/5 mr squared times omega final squared, because only one of the omegas is unknown. Okay, so now we can put in the numbers. The mass and the radius are the same for both, so that makes it easy. 1 kilogram, 1 kilogram. Okay, that cancels. 1 kilogram, 1 kilogram. That cancels. That cancels. So you just have 2/5 times 4 radians per second, right? And that's equal to what? 4/3 minus 2/5 omega final squared. If I multiply everything by 5, no, if I multiply everything by 15, I'll get rid of the denominators, right? 5 goes into 15 3 times. 3 times 2 is 6. 6 times 4 is 24. Right? I don't want to have any denominator. And then you're going to have here 3 goes into 15 5. 5 times 4 is 20. 5 goes into 15 3 times. 3 times 2 is 6. Then I can simplify it, divide everything by 2. Okay, this is my second equation then. This is my first equation. Now let me impose kinetic energy conservation on the system. Now all 3 of them are conserved, you see? So what's the kinetic energy? Kinetic energy of this guy is, or kinetic energy initial is equal to kinetic energy final of this guy plus the kinetic energy final of this guy. Right? But remember, we had derived an equation for the total kinetic energy of the solid sphere. What was that? I said derive a combined equation 5/6
Yeah.
mv center of mass squared. Right? And then kinetic energy final of this one, or yeah, this one is going to be 5/6 mv1 squared, right? Then kinetic energy of this guy, that one's a hollow sphere, right? What was the combined kinetic energy of that one? Oh, hollow sphere we didn't do, right? How do you derive that quickly? 1/2 mv squared plus 1/2 2/3 mr squared omega squared, right? So you should be able to derive these even in your sleep. Like that. 5/6. Well, the hollow sphere was 5/6.
Your total was.
Solid was something else. The hollow sphere is the 5/6. but the hollow sphere is 2/5 here, right? 1/2, 1/2, 1/5. The solid sphere is 7/10, right?
Right.
Because it's 2/5 moment of inertia, so it's 1/2 plus 1/5, which is going to be 7/10. So the solid sphere is not 5/6. The hollow sphere is 5/6. So then it's going to be 7/10. Right? So then what goes here? Oh, where should I write it? Well, let's just write it here. 7/10, mass is 1. VCM of that one was what? 30 squared. 7/10, 1 kilogram. What's the VCM of this one? Well, we don't know. V1 squared. And then 5/6. This one, mass was 1. V2 squared, we don't know. There you have it. So we have wait a minute, that doesn't make sense. If that's the case, I can just use these two equations. If this is my kinetic energy equation, I can just use these equations, combine them to get V1 and V2, but then how do I solve for omega final? Because
Yeah,
omega final doesn't
can
have
solve.
V.
Radio?
Huh?
Oh, that's negative. Right? No, no, no. Yeah, that's negative.
Wait a minute, there's no variable here? Is there no variable?
Supposed to be.
Huh?
Supposed to be a variable.
No, I think
Because they gave us the angular velocity of that, huh?
Oh, then we can properly like change. That's 4 radian. That's the initial angular velocity for M1, but for M2,
The problem gave you that. The problem
Too much.
gave you this is 2 radians. Because remember, there were potentially 4 unknowns. This one, the omega, and this. But 4 unknowns is impossible to solve if you have 3 quantities to conserve, right? But then this equation ends up having only 1 unknown. So what's 12 minus 10 is 2. Oh, wait, omega final? Why is it squared? Dang it. It's not squared. Angular momentum depends on its I omega, right? I omega initial. There's no square in it. So this one just should be I omega minus I omega. So no square.
now you can solve it.
Well, now you can actually just solve it without even using another equation. Just omega final is what? Negative 2/3, which means actually it doesn't change its spin backward. It still continues spinning forward, right? But slower. If it was going forward, it goes slower. Okay, but then now I am. Hold on. Oh, okay, then that's it. I already know what this is, and then I can combine these two to figure out V1 and V2.
Wait, I have a question. So that's 7/10 MVCM squared. Is VCM equal to V tangential?
I purposely made a large mistake in this
Here
to
we
want
go.
to see who can catch it.
Because like when you throw it, the angular velocity is not consistent to its velocity of center of mass.
Because
So-
somebody randomly can give it a spin, right?
Yeah, you cannot say like it's not like just it's going like downward. because
Yeah.
I give you a
Let me see if
spin.
I'm a baseball pitcher.
Yeah.
You
see
know,
that?
some random spin, right?
Yeah, I should try out for baseball.
Now you cannot use that formula to solve it.
Oh, so I
Seven
can only use that
one half
one,
MV,
I can only use, you're saying I can only use the,
1/2 MV.
yeah, I can
center
only
of
use
the
this
square
total energy when it's rolling on the ground.
when it's rolling on the ground.
So then what can I do when it's rolling in the air?
No, you have to separate them.
Oh, I have to separate them. Okay, so then, okay, so all of it is wrong. But you know what though? You could have solved it the way that we just did it. You could have solved for V1, V2, and then this gave you omega final. So there was nothing in that problem that would help you catch your mistake. You got V1, V2, and you got the omega final, and you think you're done.
But actually,
But you're wrong.
yeah.
Right? So you need to do what then? Half m VCM squared plus half I omega initial squared equals kinetic energy final, half m V1 squared plus half I omega final squared plus half m V2 squared plus half I2 omega final squared. You see? So each, the translational and the rotation is separate. They're independent from each other. Right? So then, okay, I put mass is 1 here. Okay, I get rid of the half. I put the mass is 1. The initial velocity is 30. The initial moment of inertia is what? Solid sphere, 2/5 mr squared. But since the m and the r are 1, they disappear. Omega initial is 4. So that part's easy. Then you got m, which is 1. V1 squared, we don't know. Moment of inertia is 2/5. mr squared becomes 1 again. Omega final, we don't know, right? And remember, for kinetic energy, it doesn't matter which way it's rotating. Then we get here mv2 squared, so that's 1 again. And then v2 we don't know. Then I2 is going to be 2/3, right? Because it's a hollow sphere. mr squared becomes 1 again. And then omega final is 2.
And 2 squared.
Oh, this time you get omega final in there.
And
We
then
didn't have that before.
Right.
But over here we already solved omega final.
Very good.
So then we could substitute that in there.
Solve
So
V.
this equation alone, we are still correct here. We're good. Because there's no other angular momentums in this problem. So it's actually not that bad of a problem, right? So you just have here 900 plus 16 times 2, 32 over 5 is equal to V1 squared plus 2/5. Omega final, I'm going to put negative 2/3, right? And then I'm going to square that. Plus V2 squared plus 4 times 2, 8/3. Okay, so then this one, you can combine all of that and get a number. So you literally have now 30 is equal to V2 minus V1. And then the kinetic energy is going to be whatever this number is. When you square this, it's still going to be positive, right? So then minus 4 times 2 is going to be what? 4 times 2, 8 over 9 times 5 is 45, right? So 8 over 45 minus 8 over 45. Then this one goes to the left and still you subtract. So these are both positive answers. You subtract them from that. So then you get minus 8 over 3. and you get basically 903.5555. 903.5555 V1 squared plus V2 squared. Then you can substitute this, put it into there, and then solve for V2 is equal to 30 plus V1. I'm going to put that in solver. V1 is negative 30. V1 is negative 30. Oh, no, V1 is negative 30, no. That's the original, remember one of the answers comes out equal to its original velocity. So if I get V1 is negative 30, remember I had set the V1 to be going backwards, right? I get V1 going back and V2 is forwards. So if I get V1 is negative 30 as one of my solutions, that means that's the same as the original answer. So I ignore that. So then I look for my other answer.
I actually got.
And the other answer is 0.059.
Yeah, 0.05.
So what does that mean?
That's really slow.
Oh, you know what? It's a rounding error. It's actually should be just 0.
Yeah,
Oh, wait. That's.
if that's 0,
Oh, it comes to a stop.
suddenly.
It comes to a stop. You know why? Their masses are the same.
Oh, that makes sense.
When two objects, remember the momentum collision problem we did in class? When the red gliders
That's
come,
gonna-
one, and this is stopped, this comes and hits it, and then the other one goes.
There we go.
Yeah, it should stop.
But just.
But it stops, but it keeps spinning.
Yeah.
Like a pool.
on a
Like
stop.
Yeah. It just goes like this, hits it, stops, and then slowly spins, right? In the same place, right? And because the omega we got was negative, it means it keeps spinning in the same direction. Oh, wow, 2/3 radians per second is the spin rate. So it slows down quite a bit, but it just spins. And then the next ball goes forward and spins. Oh, but remember, this is assuming that the omega of this was 2. So I had to give you that information. So then what else? We can now put that 0 back into here, and then so for V2, well, V2 is 30. So if I had told you the omega of this was something else, like 3, let's say the omega of this was 4. Oh, depending on what omega I had given you here, that's gonna change the,
Yeah.
oh, okay, I see what that's gonna do. Depending on what omega I give you here, that's gonna change the omega of the ball. Right, if I tell you the omega of that was 4, and this is also 4, what's that gonna do? Is it gonna stop and not spin?
Yeah.
Oh, but they have different shapes. This is hollow sphere, this is solid
All
sphere.
different shapes.
So like if I gave you the omega is 4, what would happen? I'll put 4 here, right? And then what would that change? Then this would be 8 instead of 4, right? Because I'd given you that it was 2, right? So it'd be 4 times 2 was 8. Then if I multiply everything by 15, this one would be
40.
24. This one would be 5 times 80, 40. This one would be 6. And now what would omega be?
12 minus 20.
Negative.
3 point. Oh, now we get positive. No, not 3. 2.666 radians per second. So now it comes, this starts spinning and going forward at the same speed. This one stops, but then spins backwards at 2.66 radians per second. So it depends what happens, how they hit each other. This one hits this one. If this spins at the same rate, this gotta spin backwards. But the stopping, it has to stop because they're the same mass.
Which way did it spin? That one we.
Which one? Because since omega I got positive,
Yeah.
that means it does spin backwards. Remember, because I'm putting negative here in the angular momentum. I'm already assuming that it's spinning backwards. So if I get omega negative, then it's still spinning forward.
Yes,
but if
still
I get
spinning.
omega positive, it is spinning backwards.
Okay.
So that means if this spins forward very fast, this gotta spin back to make up for that. You see? But if this is not spinning forward too much, then this has to still spin forward. It makes sense. Depends on how they come and hit each other. If it hits you that, and this one starts spinning very fast, then this one gets a backward kick, right? Okay, let's do 10 minutes of statics problems. Statics. You're gonna have a whole semester of statics when you take engineering course called Engineering 131. But we do it in 10 minutes here in physics. No, we'll give it some more time next week. But we'll do this kind of problems like statics, things that are stationary. Much easier problems, much easier, right? Okay, so we can start the video.